Okay, looks like we're going. So, here's what we were talking about last time. Well, last time before the exam, of course. Quick side note about the exam. So, y'all all noticed, previously discussed, of course, that we had some multiple choice questions on the exam. I am currently soliciting feedback on multiple choice. I see some head shaking. Yeah. Some thumbs down. Okay. Not a fan. Okay. If you want to stick around for a minute afterwards, I'm very interested in hearing your specific thoughts. And if you can just hang out for a couple minutes after class if you want. Not required, of course. But anyway. Okay. So we were talking about this seemingly kind of odd question here about the rate that fluid flows along the curve. And even weirder, it was phrased as, okay, well, let's think about all of the fluid that is within a kind of a certain cross-section, you might say, of the curve. And the answer to, what's the total flow rate? This total flow rate that this fluid is flowing along the curve was that it was this. And in particular, you'll notice that it depends. It is proportional to that cross-sectional area. Well, of course it is. The bigger the cross-section, the more fluid, it stands to reason, right? So two things. For one thing, that area is arbitrary. For another thing, this line integral is kind of why we were interested in this in the first place. I made this assertion that if we answer this seemingly uninteresting question, that line integrals are going to come up as part of the answer. Right? So I think it makes sense to interpret the answer as thinking about this area as kind of dividing over to be in the, if you will, the denominator over here. And so I want to interpret, this is how we ended it last time, that what this is telling us is an interpretation of what vector line integrals mean. Right? Our very first experience with line integrals was that it computes work. Okay, well, it computes work when the vector fields represent forces. So here we have an interpretation of line integrals where the vector field represents something entirely different, namely fluids. And the answer is that line integrals, in this fluid context, it tells you, okay, per unit area, of course, right? This area, the bigger the area, the more, obviously per unit area. But it's telling you how much the fluid is flowing along the curve. Right? And so this is the interpretation that I want to take here of line integrals, or said differently, this is our real sort of like conclusion. This is what we care about from this calculation. We don't actually care about little tubes of fluid. Right? What we care about is that we now have an interpretation of vector line integrals in the context of fluids. Okay. All right, so picking up from there, here is a related idea. I'm going to talk about something called a closed curve. A closed curve just means that it starts and ends at the same point. So, for example, this curve here you can think of as starting there, I suppose, and then if it starts there, then it ends also there at the same point. Okay, this is called a closed curve. So, in this case that you're looking at a closed curve, this line integral, we're going to give a different name to the interpretation, and the name is circulation. And I think this actually makes a lot of sense if you sort of think about what's actually going on here. Keep in mind we have a closed curve. And if you have a closed curve, it doesn't necessarily itself have to be a circle, but if you keep track of the direction vector, right? So this curve here, let's say it starts there, the direction vector, that unit tangent vector starts pointing up. As you go around, that unit tangent vector, let's just save my wrist here, that unit tangent vector makes a circle, right, eventually. So independent of the shape of the curve, that unit tangent vector goes all the way around in a circle. So if we're measuring, keep in mind what we already know about these vector line integrals. If we're measuring how much the fluid is flowing along the curve, and if the curve is making a circle, right, then kind of by sort of transitivity, if you will, we're measuring here the extent to which the fluid also kind of goes around a circle. Right? So this term circulation makes sense from that point of view. So anyway, that's why we call it circulation. Circulation just means line integral around a closed curve. All right. So here's some examples. We have here a closed curve. Now keep in mind, if we're talking about curves and we're talking about line integrals, remember to compute a line integral, you need to know which way you're going along the curve. I said differently, curves now are oriented things. So this is an oriented curve, so I can't just draw a circle. I have to draw a circle with the understanding that we're going this direction, let's say, around that circle. Okay. Now, to what extent does this vector field flow along the curve? Well, you can see from the way this fluid is flowing, anywhere you might happen to look, the fluid is flowing very much the same direction that the curve is going, right? So this fluid is flowing entirely with the curve. So there's a positive amount that the fluid is flowing along the curve, all the way around the curve. So you would expect then for this circulation to be positive. Positive circulation means that yes, indeed, there's quite a bit of fluid flowing around the curve. Okay. Now, for comparison purposes, let's look now at this curve. And it looks like the same curve. And in fact, confession, when I drew this, what I really did is I copy-pasted from here. I copy-pasted it. So it's exactly the same curve, kind of, except now notice that this one is oriented the other way. Remember now, curves, we have to actually talk about oriented curves. As an oriented curve, this is totally different from this curve. They have different orientations. They are different oriented curves. Okay, so to what extent is the vector field, and this is literally the same vector field now, to what extent is this vector field flowing along the curve? Well, it's quite the opposite, isn't it? Right? The curve is going that way. The vector field, the flow of the fluid is going the opposite direction. We're going to have negative dot products inside of this integral. Right? And so, is the fluid flowing along the curve? Well, again, no, quite the opposite. Indicated by here we would compute circulation being negative. Everybody see what we're talking about there? Okay. All right. Okay, and now let's look at this third case. This third case is kind of a weirdo, at least at a glance. But then again, in the real world, things don't look nice and lined up and perfect like these first two examples, right? In this third example, for some parts of the curve, the fluid is flowing opposite of the direction that the curve is going, right? The fluid over here on the left, the fluid is flowing upward, I guess you might say, right? Whereas on this part of the curve is going downward, you might say, right? So you would expect negative line integral, at least along in this part of the curve, whereas over on this side, the fluid is flowing up. The curve over here is oriented up. So you expect sort of positive terms over on the right, negative terms on the left, and there's going to be sort of a balance of some sort, and it's either going to lean positive or lean negative depending on which one of those is bigger, right? And by how much and over what length, and you just got to evaluate the integral. So here, the way it's drawn here, circulation here, not clear as to whether it's positive or negative. If I had to guess, I'd guess positive. I feel like the positive part looks bigger. But anyway. Okay. Alrighty. By the way, another way to think about this circulation, and I think this is a nice point of view, circulation suggests I'm going to assert which way a small object would rotate if you were to drop it into the fluid. So, for example, let's imagine this is all very small scale. This is all very itty-bitty little stuff. And let's suppose that I were to drop a leaf. Say, this is the fall and leaves are orange, right? Suppose we were to drop a fallen leaf into a puddle, a little stream, whatever it is. Which way do you think this leaf would spin? Right? I mean, it's going to spin the direction that the fluid is pushing it. The fluid is kind of circulating counterclockwise, so we would expect this to spin counterclockwise. And same thing over here, in fact. It's just that the signs would, oh gosh, sorry, that didn't work well. The signs would be backwards. Here, this leaf still flowing counterclockwise. The fluid, after all, still going counterclockwise. Right? But we would call that negative here because the orientation of our curve, the orientation of our boundary curve being clockwise, right? You could phrase circulation as asking the question, how much is this leaf flowing clockwise? Answer, well, it's flowing negatively clockwise. It's flowing counterclockwise, so that's a negative clockwise. Does that make sense? Yeah, question.
Does that mean the circulation is zero if there's like a path along the vortex?
If there's a what now?
If there's a path along the vortex.
Path along the vortex. Oh, you talking about the center spot here?
Yeah.
Yes, there's a bunch of detailed devils that we would have to, that's going to depend a lot on specifics. Right. I just want to talk here about the general intuition of, in the simple case where it's pretty clear what's going on, just to make the connection between circulation and rotation. Yeah. So, yeah, I mean, you ask a great question, but it would, in order to answer it, we'd have to get a lot of specifics down on paper. Yeah. Okay. All right. So, moving along, in terms of computing vector line integrals, sometimes you get lucky. In those situations where you can get lucky, take it. Right? So I'm just going to show you an example of the kind of good fortune that can come your way. Here's my example. We have a parametric curve. Notice the curve is parametrized kind of in spherical coordinates. Right? So we've got here rho, phi, and theta as functions of time. Which means that x, y, and z are going to be even uglier formulas. Right? I mean, x as usual, rho sine phi cosine theta, y is rho sine phi sine theta, etc. And so those are going to be nasty formulas. The actual position as a function of time, nightmare. Notice though, because rho is 1, this curve, whatever it is confined to the surface of this unit sphere. Right, so it's stuck on rho equals 1, and so this curve is it's like it's moving along the surface of the Earth, or something like that. Okay. All right. Next thing I'm going to point out. Now you could compute this by brute force, and I really don't want to, and I really advise you not to. I think it'd be a nightmare. I'm not even sure it's tractable. It'd be a monster. But here's the next thing you can observe. Our vector field here, notice the vector field is literally a scalar multiple of the position vector x where you're evaluating it. So that's really invaluable information. That means that wherever you are, the field vector is parallel to your position vector. All right, so these are a couple of observations, all kind of centered around the fact that this is a sphere. Okay. So how you capitalize on this works out really great. If you know that you're on the surface of a sphere, that means that your differential, your position differential, your dx vector, this thing right there, that dx, parallel to the sphere. Right? If you're stuck on the surface, then your direction vector is parallel to that surface. Next cool observation, the field vector, because it's parallel to your position vector, notice your position vector, and this being a sphere, think about the symmetries of the sphere centered at the origin. The position vector is always perpendicular to the surface, and that means that my field vector is always perpendicular to the sphere. Right? So now look at the integral that we're actually interested in. I need to know about f dot dx in that integral. Well, of those two things, one of them is always parallel to the sphere, one of them is always perpendicular to the sphere. That means that they're always perpendicular to each other. That means that dot product is 0. That means we're adding up a bunch of zeros. That means our answer is 0. And we're done. No nasty trig. Right? No ugly integrals to compute. Just boop, 0. What do you think? Yes?
Could you please explain why the x is always parallel to the sphere?
It's always perpendicular. So the position vector x is always perpendicular to the sphere. And this is just a geometry thing. So spheres, if you draw a line from the center of the sphere out to the edge of the sphere.
I know this,
right?
But I don't know the first point.
Oh, the dx part.
Right.
Oh, yeah. So if you're on any surface, right, if you're confined to that surface, then your velocity vector is also parallel to that surface. Because if it wasn't, then that would take you off of the surface.
Oh, okay.
That's all. Yeah.
Okay, makes sense.
Okay, good. All right. Great. Okay, so really nice little trick. The geometry is convenient. As for, when should you look for a method like this? Honestly, I think anytime you see something that's got a lot of symmetries, and spheres are great, right? And I'm not saying this will work every time you're interested in an integral on a sphere. But I'm saying it's something that's worth kind of giving yourself a little bit of, think it through, right? Whenever something really nice like that happens. Another tip-off, by the way, is this right here. The fact that our vector field is a scalar multiple of position. That's wow, what are the odds? Right? That's a special kind of a vector field. And so something like that might be an eyebrow raiser and make you think, do I have any obvious good fortune here? Okay. All right. Okay, this next little discussion has the potential to be a long discussion, and we're not going to in this class. A lot can be said about this that just wouldn't be appropriate in Math 219. So roughly speaking, as far as we're concerned, this is going to boil down to a kind of a notational alternative. Let's develop that part of it. Y'all know from long ago this fact right here. Derivatives, of course, are computed component-wise. You can distribute the dt. And then you can look at what you got down here, and dx dt times dt, wow, it really feels like that ought to be called dx, right? And dy dt times dt, shouldn't that be called dy? Seems like these are reasonable notations down here. So what we've got all together then is an alternative notation, sort of what you might call a coordinate notation for our previously understood only in sort of a vector sense, our position differential, right? Our dx vector. So, okay, no big deal. But look what happens if you sub that in to your notation for a vector line integral. Now, all I did is just rewrite dx as in coordinates, dx, dy, dz. And, of course, your vector field is going to have coordinates. I'm going to use the usual, fairly standard PQR to represent the coordinates of my vector field. And now you can just straight up dot out that dot, right? That dot right there. You can just dot it out and you get that. So this is the alternative notation. This is a sort of a different way that you can write a vector line integral. And some people like this notation. So, alternative notation. Now, at a glance, do we like this notation? This one over here is more compact. This one over here on the left that we've been using, this is, I'm going to call natural in the sense that, the integrand, it represents something physical. It's either velocity of fluid, or it's force, or it's something else natural, right? And this dx, again, something kind of natural. This represents changes in position, right? Linear estimates to changes in position. So this is all natural and meaningful. And there's a case that could be made that part of the reason that this is longer and clunkier is because we're breaking it down into stuff that's relatively less natural. What is P? Does P represent force? No. P is representing, it's one of the components of a vector that represents force, but P by itself, it's not exactly, it's a component, right? I mean, it's just less of a natural thing. So, for our purposes, most of the time, this notation is just not as useful as that notation. I mean, there's going to be occasional counterexamples. But most of the time, this is not a notation we're going to use. So why am I showing this to you? Right? Why am I showing you a notation that I don't recommend in this course? Well, a couple of reasons. For one reason, this is a good cultural broadening thing. This really is a fantastic notation in other contexts. If you go into a more sophisticated, if you do the differential forms, that by the way you can get a quick preview glance at if you look at our chapter 8 in the course textbook. They do quite a bit of stuff with differential forms there. And it's extremely powerful and very important for that reason. And this is what differential forms look like. This is a kind of a quick and dirty version of, to call them differential forms, we'd have to do much more groundwork. But so it's of more mathematical culture interest. The other thing is, because of this, because it's so natural and powerful, a lot of people like it. Right? There are plenty of books out there where they write line integrals in coordinate notation. That's just how they do business. Right? And so you need to know what this looks like so that when you see it outside of this course, possibly even in this course, but more likely outside of this course, right? You can make a reasonable interpretation of it. And in particular, what you're going to do, if you see this notation, remember that these, what you might want to call integrands there, right? What they really are, those are the components of the vector field that is the, what you might call the actual integrand of the vector line integral. Okay, does that make sense to everybody? Okay. All right. Okay. So heads up, just be on the lookout for that kind of thing. All right, so on to section 6.2, new topic. In fact, this is not just a new section, new topic, but this is going to be a kind of a new, we're into a new part of the course, arguably. Green's theorem is the first that we're going to see of a category of theorems. There's like 5 or 6, depending on how you count, different theorems that all have certain features in common, and that all, the more that you understand one, the more that you can use that to help yourself understand the others. So this is really just the first example of a line of reasoning, sort of a strategy of reasoning that's going to pay off massively over the next couple of chapters. Right. So this being the first example, I think it's really important to look at this, carefully. Okay. So, the thing is, there is a bunch of groundwork that has to get laid to look at this the right way, the way that I like to look at it anyway. I want to call that the right way. Right? And I want to lay that groundwork first. Okay, so the first thing we need to do is I need to reinterpret the word boundary. Now, y'all, I think you know basically what a boundary is. A boundary is it's the edge of the thing. It's the line between region that you're interested in and not the region that you're interested in, right? It's the edge of what you're looking at. Okay. Importantly, going forward, henceforth, a boundary is going to be an oriented thing. Going forward, all boundary, this word boundary itself, anytime you hear the word boundary, you should think, okay, that's an oriented boundary. And so we have to make a convention as to which of the two possible orientations should we pick. And this is an arbitrary choice, but it's very standard. And as such, it's not really optional, right? We have to kind of do things the same way that everybody else does. And here's the rule, arbitrary though it is. The rule is, if you are looking at the boundary curve, so for example on the left here, this is part of the boundary curve, part of the boundary of, my solid region there. Which way does the orientation go? It goes in the direction such that as you go that way, the region whose boundary you're interested in is on the left. Right, so you have to imagine now, pretend like this is a flat surface, right, horizontal flat surface, and imagine that you're walking along this boundary curve like it's a little path, right? And as you're walking along, notice if you're going the direction that the purple arrow goes, then the region really is on your left. Does that make sense to everybody? Right. Whereas if you did it the wrong way, right, if you walked this way, the region would be on your right. That doesn't follow the rule. The rule is the region needs to be on your left. That's the rule. Okay. If you were to look at a different part of the region or part of a different region, boundary curve again is kind of, it's where it's the edge, if you will. Which way do we go from this point? Well, we have to go that way so that as I'm walking along the curve in this direction, the region is on my left. Okay. So on the left this time has you going that way. So the thing is, notice, depending on which part of the boundary of your region you're talking about, it's not always to the right, it's not always to the left, it's not always up, it's not always down. But it's always so that the region is on your left. Okay. Now, there is a different version of this, kind of, sort of, that's very popular and is also a little bit unreliable. It is tempting to say, all right, here's a solid two-dimensional region, and here's the boundary. And notice, wherever you might happen to be on this curve, going in the direction that puts the region on your left always has you going counterclockwise. Oh, whoops. Elbow. Always has you going counterclockwise, doesn't it? So sometimes it gets misstated as, always go around the boundary counterclockwise. The reason you can't trust that is not all pieces of boundary are actually on the outside boundary. And so it's a little bit of a weird counterexample, but if you come over here and look at this region, which takes too long to color in here, close enough. If you look at this piece of boundary curve, that piece of boundary curve right there, notice you'd have to go that way in order to have the region on your left. And notice that going that way has you going clockwise, not counterclockwise. Everybody see that? So beware this whole counterclockwise oversimplification. It's just not always true. Okay. All right. So that's our convention. Okay, now we're going to set that aside. We're going to go to a new, different idea that we're going to need, something that's important to the development of Green's theorem, the way I'm developing it here. And that is this idea of accumulation. Now, we've talked about accumulation in the past. In some sense, all integrals that we compute things with are using the idea of accumulation. If you have some whole that you're trying to compute, you chop it up into little pieces and argue that the whole that you're trying to compute is the sum of what you would compute individually on individual parts, right? Okay, so chop it up, add it up, right? So double integrals, triple integrals, it's all doing a sort of an accumulation. So said differently, whatever it is that you're computing on the whole, if you compute it for just the left piece, and if you compute it for just the right piece, then this piece plus that piece had better give you the whole. Now, this is very clear for certain kinds of quantities. Let's suppose you're talking about how much mass. Right now, is it true, I ask rhetorically, that the mass there plus the mass there, does that sum give you the mass of the whole? Well, of course it does. There's only so much mass, and you can draw little lines and separate it out and however you sort of like, but the mass doesn't just disappear. And the mass doesn't spontaneously generate, right? There is a conservation of mass, and so mass has this feature that I like to call accumulating. So mass accumulates over the area, or you can say mass is an accumulating quantity. All right, now this seems like a silly observation. Well, of course mass of course mass doesn't just disappear. Of course, same thing can be said of everything else we've done an integral with. We've computed work, we've computed populations, various other things that we've computed with integrals. They all have this feature. That's one of the big assumptions that goes into integrating. Let me point out, though, that not every quantity of interest has this feature. Perimeter does not accumulate. Easy demonstration. The perimeter of this left piece is the length of that blue curve. There's the perimeter of the left, right? The perimeter of the right piece is the length of this orange curve. Is the left perimeter plus the right perimeter, is that equal to the perimeter of the whole? Is blue plus orange equal to purple here? No, of course not. Right, look at you made perimeter when you drew this little line here. Right? So it's just not. Perimeter is not an accumulating quantity. It does not have this chop it up, add it up feature. You just can't, it doesn't work. Everybody good? Okay. So the point to this is to make the case that accumulation is a special feature, right? This works for some kinds of quantities and does not in general for general quantities. Okay, so let me show you an unexpected, I'm going to call this an unexpected accumulation. It turns out that boundary circulation is an accumulating quantity. Boundary circulation accumulates. And now I owe you an explanation for that. Here's my argument. Let's suppose I have a vector field, I have a region, and I want to talk about the boundary circulation. Well, let's start by looking at the boundary circulation on the left half. Now keep in mind, boundary circulation is an oriented thing. So boundary circulation means a line integral computed around that green curve, right? Keep in mind, boundary. Got to follow the rules of orientation concerning boundary. Boundary goes like this. The boundary circulation on the right piece. Again, an oriented thing. There's the boundary circulation on the right piece. And again, I ask, is the green circulation plus the blue circulation, does that add up to the boundary circulation on the whole, namely this purple? is green plus blue equals purple, and it's pretty tempting to say, no, again, when you drew the slice here in the middle, you created line, there's more line integral stuff happening in here that's not represented at all in the purple, right? Now, a lot of the green lines up perfectly with the purple. A lot of the blue lines up perfectly with the purple. But what about all this stuff in between? And just to keep it simple, let me draw just that part. What about that line integral and that line integral? This is, in some sense, what's left over. This is the difference. This is what's making it not accumulate, or so one would think. But then notice something really wonderful about these two little pieces of line integral, what I have here in green, what I have here in blue. They're over the same curve with opposite orientations. Which means, same curve opposite orientations means that these two pieces have exact negative values of each other, and therefore they add up to 0. Right? So these two terms cancel. And therefore, that being, this was what was keeping boundary circulation from being an accumulating quantity, and it's gone. It's not there after all, at all. So, in fact, boundary circulation accumulates. Everybody see what I'm talking about there? Okay, so this is a huge point, a really important idea. That's why orientations matter on boundary. Right? We have to talk about having a convention, a specific convention on what we mean by the orientation of a boundary, so that we can have this one and this one specifically going opposite directions, so that they'll cancel. Right? And that's why it's important that it be circulations, right? Line integrals, because they are oriented things and therefore have the opportunity to make such a convention. Okay, so boundary circulation is an accumulating quantity. And if you think about it, getting ahead of myself. So I'll point out that this edge disappeared because I was going one way as part of the boundary of one side, I was going the other way as part of the boundary of the other side, and that's why we had a cancellation, right? Well, the same exact thing happens no matter how many interior pieces you have. If your solid region is like this, and, the boundary is whatever, no matter how much you slice it, let's take this edge right there. Right. Well, that edge, as part of the boundary of the piece on one side, it's going. I better use a pencil. As part of the boundary of the piece on the one side, it's going that way. As part of the boundary of the piece on the other side, it's going the other way. And so this little edge here is going to appear twice in the summation with opposite orientations, and it cancels. And so does this edge. Twice with opposite orientations cancels. This edge here, twice with opposite orientations cancels. All of these interior edges will cancel for the equivalent reasons. So slice it up all you want. Boundary circulation accumulates. Okay. All right. So, that means that if we come back to this picture here, right? I made the case that mass has this feature of accumulation, and so the mass on this side, the mass on that side. When you add them up, you get the mass of the whole. This is how mass behaves, and I'm saying now that boundary circulation behaves the same way. Boundary circulation behaves like mass. So as follows. You can look at this picture here. We can measure a boundary circulation, whatever that might happen to be. Let's say that this adds up to 33, I claim, the way I have this drawn. I'm going to ask the question, where in this picture is that 33? Where is that circulation located? And it's tempting to say, well, it's the purple. It's because that's where you measured it, right? We measured the boundary circulation along that purple curve. But the thing about it is, that 33 is the sum of that circulation plus that circulation plus this circulation plus all these other circulations, right? This 33, I could very reasonably think of as being, well, 7 of it is over in this green region, and 6 of it is over here in this blue region, and 3 of it is over here in this orange region. I could think of that boundary circulation that I measure on the boundary as actually being distributed throughout the interior, just like mass is, right? I can talk about the mass of a hole, but because of the accumulation feature, I can view that total mass as being, well, some of it's here, some of it's in each of the pieces as you slice it up. Same with circulation, right? So boundary circulation behaves kind of like physical stuff. It has location in the interior based on how you chop it up. And that allows us to do something really nice. And that is to talk about an associated notion of density. Now, quick reminder. What is mass density? Right? Old concept. Mass density. Mass per unit area. Right? You look at how much mass is in your whatever little piece of area you're looking at. You divide by the amount of area of that piece, and that's mass density. Right? Stuff per unit size. Quantity per unit, whatever size makes sense for that region. Or said differently, it's the thing you multiply by sizes to get quantities. Think about it whichever way you like. So, because circulation behaves the same way, circulation, again, it has a location in the interior. It's very stuff-like. We can likewise talk about circulation density. In the same way that we've previously generalized mass density, mass per unit area, we've talked about population density, number of people per unit area, right? Or other kinds of density, I suppose. Stuff in general, accumulating quantity per unit area. So that's all we're doing here. I'm just going to say, well, circulation, just like mass, just like population, circulation's an accumulating quantity. So let's talk about how much of that there is per unit area. And specifically then, let's talk about circulation. And we measure circulation like this. It's the line integral around the boundary. Circulation per unit, color. Circulation per unit area. That's another thing you can talk about just as well. If it behaves like stuff, you can treat it like stuff. Is that all right with everybody? Now, here's where I'm just going to start making assertions. This is where, and by the way, we could prove this if we wanted to. I don't think it's a good investment of time. That's just my opinion. But the formula for circulation density, here it is. I'm not going to, the proof's in the book. If you want to see it, that's fine. I'm much more interested in y'all having a good sense for what this is, right? That this formula, dq dx minus dp dy, what that is, it's telling you circulation density. It's telling you how much of the boundary circulation that we may be interested in, how much of that is there per unit area wherever you might happen to be looking. So that, I think, is more important than the derivation of the formula. That's an opinion. Okay. Yeah. And then notations. I like to call this Green's operator. I've never had anyone not know what I was talking about when I said Green's operator. Anyway, it's not a super popular term, but anyway, I think it's a natural thing to call it. Most of the time that I've seen Green's theorem written down, this quantity doesn't usually get given a name. It's just, this is the formula. It's the formula that's in the middle of Green's theorem that we're about to get to. So I think it deserves a name. I call it Green's operator. With that in mind, I made up this notation. We'll see if it catches on. If it does, I'm taking credit for it. GRN, right? Suggestive of the name Green. Nice and compact, though. I didn't want to write out all the E's. Right? I think GRN is enough. Right? Rote. This is a great notation. I like this notation quite a bit. ROT, short for rotation. Let's take a look again and remind ourselves, what is this thing anyway? Right? This thing that we're calling rote F, this formula. Well, it's circulation density. It's circulation per unit area. And what does circulation measure? Circulation is measuring the extent to which the fluid is flowing around a closed curve. It's the extent to which the fluid is kind of going around in a circle. In a way, the extent to which the fluid is rotating, you might say. Right? So this is a great idea for what to call it. Root. Reminder, this is another observation I made back here. Circulation measures how much the little leaves that you dropped in the surface of the puddle, how much of those leaves literally rotating. Right? Natural choice. All right, now a couple of notations that I'm not a huge fan of. Some people call this curl. The thing that I'm uncomfortable with about that is the previous notion of curl that we've talked about was three-dimensional. This is two-dimensional, right? Everything here is in two dimensions. We're talking about areas, and their boundaries are curves. This is an intrinsically two-dimensional discussion. The existing thing that we've called curl is also circulation density in a way in that context, but it's sufficiently different because of the three-dimensional context. I think it's awkward to use the same name to refer to two very different things. Recall, for one thing, of course, curl is a vector. Three-dimensional curl is a vector. This is a scalar. So they're pretty different. Anyway, nevertheless, it's very common to call this curl, and that's fine. Here is my least favorite notation for this. Our book uses this in at least one or two places, and that is to talk about del cross. And this is where I get really uncomfortable. Again, we're in two dimensions here. There is no cross product in two dimensions. So to make sense out of this, you have to say, all right, I've got two coordinates. I'm going to pretend there's a third coordinate of 0. That's not true. If you pretend that there's a third coordinate that's 0, and then do the del cross, then you get a vector, and then you say, well, yeah, but I only want this part of it. I only want what ends up being the third part of it. And so you dot K to pick out that third part. So if you were to compute this out, yeah, you would get this. But it requires imagining that you're in a third dimension that is not there. And that gives me the willies. So, anyway, it's like I said, you're going to see this elsewhere as well. Okay, I encourage these two. And I personally tend to use that one, but either of these is just fine. All right, so we're almost ready to state the well, in fact, we are ready to start motivating the theorem. We've got all the tools. Everything's ready to be put into place. First thing we did today, we thought of this idea of circulation as being a quantity of interest. Right? We motivated the idea of vector line integrals around boundaries, namely around closed curves, as representing circulation, how much the fluid is in some sense kind of causing the leaves to rotate. Right? So, circulation, that's the first part of it. Then I argued that circulation is an accumulating quantity. Right? If it's an accumulating quantity, then the amount of whole, the circulation on the whole, is the sum of the little bitty pieces of circulation that you would get by looking at one little piece at a time. And then we have this density idea, right? That little pieces of circulation relate to little pieces of area by way of a density. Right? So Green's operator is our density, and again, take your use your favorite alternative notation to put in there. And altogether, we have ourselves Green's theorem. Green's theorem says that a boundary line integral can be computed as a double integral over the interior of Green's operator. And it's a shocker at a glance because this integral here happens only on the boundary. Only on the boundary. And yet it computes something, namely this double integral, that if you're going to compute this double integral, well, then you've really got to know what's going on inside the entire interior. Well, if this right-hand side requires knowing what's in the interior, how come the left-hand side doesn't? Right, so that's weird. Right? It's very unexpected in that sense. But powerful result. Again, this is called Green's theorem, and I will bet we are out of time here. Yep, we are out of time. So we will draw the line right here. We'll pick up and see some examples and applications on Friday. Y'all have a good day. Again, reminder, if you want to put in your 2 cents about the true-false question, stick around. I'm all ears. Y'all have a good day.